Hello everyone, we present our paper, Neuro-Modulated Hebbian Learning for Fully Test-Time Adaptation. Our major contributions include 1. We identify that the major challenge in fully test-time adaptation lies in effective unsupervised learning of early layer representations, and explore neurobiology-inspired soft Hebbian learning for effective early layer representation learning and fully test-time adaptation. 2. We develop a new neuromodulated Hebbian learning method which combines unsupervised feed-forward Hebbian learning of early layer representation with a learned neuromodulator to capture feedback from external responses. We analyze the optimal property of the proposed NHL algorithm based on free energy principles. 3. We evaluate our proposed NHL method on benchmark datasets for fully test-time adaptation, demonstrating its significant performance improvement over existing methods. The performance of DNNs tends to degrade when there is data shift between the training data in the source domain and the testing data in the target domain. Fully test-time adaptation only needs access to live streams of test samples, which can dynamically adapt the source model on the fly during the testing process. In neural network models, the early layers of the network tend to respond to corners, edges, or colors. In contrast, deeper layers respond to more class-specific features. In the corruption test-time adaptation scenario, the class-specific features are always the same because the testing datasets are the corruption of the training domain. However, the early layers of models can be failed due to corruption. Existing literature has shown that early representations learned by Hebbian learning are as well as backpropagation and even more robust in testing. This figure shows the feature maps learned by different methods. The first row shows the original image. The second row shows the images in the target domain with significant image corruption. The third row shows the feature maps learned by the network model trained in the source domain for these target domain images. The fourth row shows the feature maps learned by our Hebbian learning method. The last row, Oracle, shows the feature maps learned with true labels. We can see that the unsupervised Hebbian learning is able to generate feature maps which are as good as those from supervised learning. In this work, we first incorporate a soft decision rule into the feed-forward Hebbian learning to improve its competitive learning. Second, we learn a neuromodulator to capture feedback from external responses, which controls which type of feature is consolidated and further processed to minimize the predictive error. During inference, the source model is adapted by the proposed NHL rule for each mini-batch of testing samples. Our proposed neuromodulated Hebbian learning consists of two major components: the feed-forward soft Hebbian learning layer and the neuromodulator. The soft Hebbian learning layer aims to learn useful early layer representations without supervision based on local synaptic plasticity and soft, competitive learning rules. It is able to generate early representations which are as good as those learned by end-to-end supervised training with labeled samples and backpropagation. During our experiments, we find that this soft Hebbian learning layer can significantly improve the performance of the network model in the target domain. However, we recognize that the feed-forward Hebbian learning only is not able to achieve competitive performance as the current state-of-the-art methods for fully test-time adaptation. We find that it lacks the capability to effectively respond to external stimulus, specifically the feedback from the network output layer. To address this issue, we propose to design a neuromodulator layer, an intermediate layer or an interface between the soft Hebbian learning layer and the classifier module of the network. This neuromodulator layer is updated using backpropagation with the entropy loss being evaluated at the network output. It serves as the bridge between two different learning approaches, the feed-forward Hebbian learning and the original error backpropagation. To approximate the true distribution Pty(xt) by a posterior approximation, one can consider the similarity between these two distributions measured by the following Kullback-Leibler KL divergence. This minimization of KL divergence can be converted to minimization of the free energy F, defined as following formula. As discussed above, the early feed-forward layer aims to learn useful layer representations of the input without any supervision. An approximate solution to this problem can be reduced to finding the first principal component of the input data, known as Ojha's rule, and its variations. The Ojha's rule is itself a variation of the Hebbian rule, plus a normalization condition. The problem of minimizing the KL divergence for Q2y and its true posterior Pty(xt) can be formulated based on the free energy principle, where PTXT is the normalization term. Note that this term does not depend on Q2Y. Therefore, minimizing the KL divergence is reduced to minimizing F. To this end, given a batch B of data in the target domain, we rewrite and decompose the free energy FB for current batch into the following two items. The first term is already minimized through soft Hebbian learning, while minimizing the second term requires the likelihood distribution PTBY. We minimize the entropy of Y given the current batch B in a discrete way as the following formula. The classification errors in the highest severity level corruption test datasets for test-time adaptation are reported in following tables. First, we compares the classification error of our proposed method against recent test-time adaptation methods on the CVPR-10C dataset. Our method performs better than other baselines with the three backbones including ResNet26, WRN2810, and WRN42, indicating the effectiveness of the proposed test-time adaptation method. Very encouraging results are also obtained on the large-size complicated ImageNet-C dataset, as shown in follows. Figure in the left side compares the feature distributions on corrupted data obtained by different adaptation methods, including the source model with no adaptation, the tent method, and our method. We also include the feature distribution for the supervised learning with the labeled sample, denoted by Oracle. We can see that our method is able to learn features that are close to those obtained by supervised learning. The mean adaptation error of the full test dataset on Gaussian noise of CVPR-10C in the different adaptation stages is shown in right side. We can see that our method outperforms the norm and tent methods after the fifth batch test time adaptation. This implies our method can reduce error faster given few testing samples. Results for digit recognition from the SVHN to NIST, NIST-M, and USPS datasets are also reported in right bottom. We can see that our method achieves the lowest average error when compared to other test-time adaptation methods. In summary, we identify that the major challenge in fully test-time adaptation lies in effective unsupervised learning of early layer representations, and explore neurobiology-inspired soft Hebbian learning for effective early layer representation learning and fully test-time adaptation. We develop a new neuromodulated Hebbian learning method which combines unsupervised feed-forward Hebbian learning of early layer representation with a learned neuromodulator to capture feedback from external responses. We analyze the optimal property of the proposed NHL algorithm based on free energy principles. We evaluate our proposed NHL method on benchmark datasets for fully test-time adaptation, demonstrating its significant performance improvement over existing methods. Thanks for your watching and listening.